I hope that from the yesterday session you remember that what we studied is uh, the choice how we can mix between the parametric and the non-parametric test. Once again, before to go further, I will just show that what we did. We have seen that what are the assumptions when we are doing the parametric test. If you can see my screen, okay, if you can see my screen, yesterday I talked about t-test and then ANOVA. So t-test when you have to compare two groups and ANOVA when you have to compare more than two groups. Within t-test, you have two different kind of possibility or inferential statistics options. One is independent sample t-test or paired t-test. I will talk again that what does it mean. But before that, ANOVA also have two options. One is that you perform a normal ANOVA, either one way or two way. One way means if you have only one factor. Two way, it means that you have more than two or more than two factors. If the data is following the assumptions of the parametric test, that is, the samples are independent, samples follow the normal distribution, there is a same or the equal variance among the different groups within the sample, there are no outliers, and if the sample size of all the groups are similar. If these assumptions are met, what you will do is you will do the independent sample t-test, or otherwise if you have more than two groups, you will compare it either with the ANOVA one way or two way, right? However, there are certain conditions when you measure the variables before and after the treatment. It means that not between the two groups, the same group you are measuring, the variables you are measuring before and after the treatment. In that case, your data is not independent anymore. Or otherwise, sometimes you do the experiment several times with the keeping experiment and the control treatment in parallel. It means that you keep on taking the reading or you keep on taking the observation or the data points even when the experiment is kept on running. In that case, the data does not qualify for the independent sample. If you remember from the yesterday talk, I already explained you what independent or the repeated samples are. For a quick look, you can see here that the independent sample and the repeated sample. I hope that you remember this. Now, in the case, even yesterday I said that if the data is not independent, then you have to do paired sample t-test, or otherwise as an alternative to normal ANOVA, you have to do repeated measure analysis of variance. I will explain this in slight detail in the coming slides. But before that, I just want to show you how you can calculate the independent sample t-test and ANOVA if you do have all the assumptions met. I hope that you remember that how we calculated yesterday the normality, right? Using the SPSS. So in here, using the SPSS, and I have also showed you that how you can assess the normal distribution using skewness, kurtosis, histogram, and normal QQ plot using SPSS as well as PAST. I am assuming that you are already having information or knowledge about this normal distribution. So I am going further into more detail today. But before that, you also remember that I talked about homogeneity of variance, and I stopped at a point that how you can calculate this homogeneity of variance using the Excel, right? Using the variance function in the Excel. In the day 3 folder of the files which I have shared, it's already there, the calculation with the functions in each column and the row of that Excel sheet. However, if you remember, yesterday I said that this F-test for the homogeneity of variance which we performed yesterday, it's good for t-test. Why so? Because in t-test you have just two different groups, right? you have just two different groups, a control or the treatment. However, once you go in ANOVA, you have more than two different groups. So you cannot just make the F test as we have done it for the independent sample t test. In that case, we will see that how we can calculate the F test for the homogeneity of the variance for ANOVA. So we will see this. Further, we will see that how we can test the null hypothesis using ANOVA and using the independent sample t-test. So maybe it is better that I will go parallelly when I am doing the experiments or the hands-on training with these slides. One important or the one different thing which I wanted to talk about is that when you are doing ANOVA, you will also do post-hoc test. What this post-hoc test means is that ANOVA will tell you that whether there is any difference, real difference exists between the different groups or not. As I said that in ANOVA you can have three different conditions or more than three different conditions or the groups. So ANOVA test will tell you whether there is any real difference between C, T1 or T2 or there or not. But it will not tell you that which particular condition is having the real difference. And to access that or to understand that, you have to do the post-hoc test where different groups, let's say that in any example you have group A, group B, group C and group D. Each different group will be compared with each other in the different possible combinations, and that is the post-hoc test where one of the most widely used tests is Tukey's test. So we will see this also while we are doing the practical. So I think instead of explaining you in the PowerPoint, it is better that I will show you parallelly in the Excel sheet as well as in the SPSS. So what you should do is that when you will open the day 4 folder in the file which I have already shared, with you, in that particular folder, you have the day 4 file, and there is an Excel sheet labeled as significance test. Okay. Now in this significance test for Excel sheet, you do have several spreadsheets. Let us go first to independent t-test, the first one. Just to remind you, yesterday we have done the F test for this particular example which I am showing you here, right? I hope that you remember that we calculated the F test and we have also seen in SPSS and passed. So after the data has crossed all the level of or possess all the assumptions which parametric test requires, we have to do t-test. Now this t-test is having a formula, or how do you calculate this t-test is that in the null hypothesis you have that the difference between the so null hypothesis says that there is a equal distance or the difference between the two tests which you are making here. In this particular example, you have control condition and you have the treatment condition, right? Now, in these two particular condition, the formula for the t-test says, right, it assumes or it requires the calculation for your variance. So you require the variance for the control sample and for the treatment sample. And here in the Excel sheet, I have given you formula which says that t-test, how you can calculate this t-test is the mean of control minus mean, or the difference between the mean of the two conditions. In this case, the difference in the mean of control and the treatment. Here in this particular box, if you see that there is a mean value or the average of the control, and similarly you have the mean value for the treatment, right? And then you calculated the variance. I showed you yesterday how to calculate the variance for uh, uh, in the Excel sheet using the variance function, right? So you calculate the variance, and now what is the two steps for the formula? First is that you have to find the numerator. So numerator here is the difference between the mean, and the difference between the mean is the mean of control minus mean of treatment. What you need to be careful is that the value has to be in positive, because anyway you are just checking the difference between the mean. So even if it is coming in negative, you can cancel it out using this mod, right? So you have this particular 76 is the 76 unit is the difference between the mean of control and the treatment. Now in the denominator, what you have is the square root of the variance divided by your N1. N1 is what? N1 is your sample in the first condition. So using this particular formula, what you get is, once you calculate, you get a value of 2.366. Like yesterday, I showed you that there is a table for F-test. There is also a table for T-test. The link is already provided you in the Excel. And then this helps you to find out the T critical value. Now this T critical value, you have to check. How you will check it? You will check it in the green color. You will see that 18 is what? 18 is the total number of sample, that is the degree of freedom of the total sample. So in each case I have 10 samples. So 10 plus 10, 20, and 20 minus 2, because degree of freedom is n minus 1. So here you have the total value of 20, total samples 20. So you subtract minus 2. So you have 18, right? And then what you are expecting, I am taking the alpha value, that is my significance level, as 0.05. So now this is it. This is your T critical value table, where you have the degree of freedom 18, right? And then two side, because we always do the two-tail test, which is more robust. So in two-tail, p-value of 0.05, 0.05 is this one. So now you see the table, this particular value, and then you have it in here, 2.10, right? The null hypothesis gets rejected, right? The null hypothesis gets rejected because our t-value, which is calculated as 2.36, is higher than the critical t-value, which is there in the table, and hence we reject the hypothesis. So whatever the difference we are seeing between the control and the treatment is real, and our null hypothesis was the difference between the two values are just by chance, right? So this we rejected, and then we can see that the inferential statistics, that is independent sample t-test, holds true, saying that the difference between the control and treatment is real. Now let us check this with, so this is the formula, and this is the Excel sheet where you can do the test in the Excel. But let us try this, and I will show you in the past software whether our calculation is matching with the statistical software or not. Now yesterday I showed you that how you can do the data entry in past. Since it is just a trial, I just want to show you whether the difference exists or how the past is taking this data. So we will just leave it because we are just considering A and B column as two different data sets. Go in univariate, go into sample, sorry. Go into sample test and then you conduct this two sample test here. Now this two sample test, right, what this particular table says, that you have a 10 number in the control which is there because we have 10 sample. Same for treatment. You have the mean of 167. We have also got 167. Variance of 84, variance of 84. Similar in the treatment B. Now, whatever the calculation it has made, now what you will see is that whether the critical t value is 2.10. We also have critical value of 2.10, what we have already calculated. So the significance test is 5.19 to the power 10 to the power minus 15. So it rejects the null hypothesis and it says that whatever the difference between the control and treatment, it is a real difference and it is not just by chance, right? You can also see, yesterday I showed you, I talked to you about the F test. Those informations are also there. I will come later about the Mann Witney and other tests which are already showing over here. So right now what you need to remember that how any software is being performing these kind of tests and what actually it uses. So on the day 1 you have seen that the variance is calculated, or on the day 3 I have showed you that how the variance are calculated, and then you will see that in all the parametric tests variance are used in the formula to find out the inferential difference or the significance difference between the two conditions. So in the two conditions, what we have covered that how we can check the normal distribution. We have covered that how we can do the homogeneity of variance using the F test in Excel as well as in the software. As well as today we have seen that how we can calculate the independent sample t-test. So here in this Excel you can see all the values and the formula, and based on the formula you can do by yourself and then match it with the past and see that the value what you have got is similar to what past software is giving you, right? So it means that the null hypothesis is rejected in this particular case. Right? Now I will also show you this particular test in SPSS so that we can check the other parameters also there. I will open in SPSS. Now here I have showed you on the day 1 that how you can enter the variables, the data point. I am not going to repeat it today. You go in analyze. Again descriptive statistics I am not going to show you. We can go directly in compare means and then select independent sample t-test. Now in this independent sample t-test, treatment is your grouping variable because the first is control and the second is the treatment. And then you have the test variable as whatever variable you are opting. No need to change anything else. And then we can go for OK. Now here again, what you will see is it has calculated the Levin's test for equality of variance. So what we have calculated yesterday was F test for equality of variance or homogeneity of variance. It is by far the most used test for homogeneity of variance. I have told you yesterday also, and this is the Levin's test what it calculates. If the Levin's test of equality of variance If it is significant, means that your two data are not following the homogeneity of variance. Since the significance is greater than 0.05, we are assuming or we are saying that our null hypothesis is rejected and the sample do have the equal variance, right? So this is how you observe the Levin's test for equality of variance. Yesterday we could not do this because in SPSS you get this Levin's test once you perform the ANOVA or student test, right? Now coming further into the next column, you will see that you have the significance here, and this significance is 0.000. So any time whenever you see a significance value of 0.00000, it doesn't mean that it is exactly 0. It is very less, that it means, right? So you can see and you can report that your null hypothesis is rejected based on the homogeneity of variance as well as on the student t-test, right? So this is how you check the student t-test data in SPSS. Now this particular slide is having more or less similar based on formula how you calculated calculated in the Excel sheet, and the link for that particular table which you can use or which you can see whenever you are performing with your own data. Now this is what we have seen when you have two samples. What if you have more than two samples, or you can say more than two groupings? Before to go into the F-test for significance, we will see F-test for homogeneity of variance. Only difference between the F-test of t-test and F-test of ANOVA is that you consider in t-test you are comparing two groups, so you don't have you don't have any other thing to, you will just check the within group variance of C and T and then find out F. Using the critical table you can match and then you can find, as I said yesterday. In this case, when you are doing the F-test for ANOVA, you have to take the largest group variance in the study and smallest group variance in the study, and that is called as F-max. And another difference is when you are using F-max, you have to use a different critical, F-critical table, which I will show you in the Excel sheet now. Again, if you go in the significance test same Excel sheet, you have a separate tab or separate sheet for one-way ANOVA. In this one-way ANOVA, what you will see is that I have given an example where you have one condition as control, the second condition as treatment 1, and the third condition as treatment 2. What you did, these are the variable values. It could be anything, whatever the variable you are measuring. What you need to do is you have to calculate the variance, and the variance can be calculated using the mean and then difference of sample minus mean, square it, and then divide by the number, or otherwise using directly the variance function of the Excel sheet, right? So this is calculated. Now what I wanted to convey here is, with this particular ANOVA data sheet, is that when you are comparing or when you are finding the F-test for ANOVA and you have more than two conditions, for example here you have three conditions, the variance for the first value is 369, the variance for the second group is 101, and third one is 71. So what you need to do is you have to consider to calculate the F-max, a ratio between the highest variance and the lowest variance group. So here you make the ratio for 369 divided by 71, and the value what you will get, this you will compare with the F critical value. And for the F critical value of this F test for homogeneity of variance, the link is already provided, and you can check in the same way. That means it depends on the degree of freedom of the variable. So in our case we have 9 and 9, right? So 9 how you get 10 values, 10 samples you have in each group. So 9 degree of freedom. So if you compare 9 by 9, and then this is alpha is 0.10. We are considering alpha is 0.05. So you will see this particular table, and you have 9, and then you have 9 here. So 3.178. In this case, 3.1789. So 3.179. Now here you have F max greater than FC value. So it means it rejects the hypothesis and sample does not have the equal variance. So what you need to understand is when you are doing this kind of test for the homogeneity of variance, here the null hypothesis is that you do have the same variance. That is the null hypothesis. And if it gets rejected, it means the sample does not have the equal variance. So what you need to do, if you want to do ANOVA for this particular data set, either you need to do the data transformation, or otherwise you have to go for non-parametric test, right? We will see that how non-parametric tests are done, but just for the example purpose, I have given a second data set which is there in the green color box, right? Here again you have control, you have T1 and then you have T2. But here if you will see that once you calculate the variance, it is 86, 101 and 71 for three different groups, right? Now again you have to make what you have to make? You have to make the difference between the largest and the smallest. So you will see that I have done a mistake in this particular column, is that you don't have to take 86 and 71, you have to take 101 and 71. So instead of taking 86, what I will do here, you can also correct in your Excel sheet here. So 1.41, right? Previously it was 1.21. So it is not a very big difference, but still the rule is rule and the formula is formula. So we can't change that. You kindly change in your Excel sheet, which is there in the Google Drive. Here again you make the difference, or you make the ratio of the largest and the smallest value, right? And then you will see that it is 1.41. So F max here, what we are getting is 1.41, right? Now FC will be same, because again you have the 10 samples. So it means you have the degree of freedom is 99. So same table you will check, right? And the value is 3.17. So in this case, you have FC 3.179 and F max 1.41. So it means that the null hypothesis is true and the sample does have equal variance. So we can go ahead with this kind of data to perform the ANOVA. Now, how will you perform this ANOVA? We will see that how it can be done in Excel, or you can also see that the Excel which is shared with you. How we do the ANOVA calculation is that we make the ratio of the among group variance and within group variance. So what this among group variance and within group variance means? So among group variance means what is the variance between the three conditions, and within group variance is that what is the difference between within the single variance. So to calculate it, what we need to do is we have to take two steps. The first step is that you have to find out the total sum of squares, which you can see in here. So total sum of squares can be calculated by sum of squares between group and sum of squares within group. So between group is this one, the first, the numerator part of the FS calculation, which you can find it out by calculating the total sum of square. Here you will see that in the two column, that is sum of square of groups, you make the mean. If you click on this particular value, you will see that the average or the mean is taken only for C, right? Similarly, you make the you find the difference of this particular value with the mean. That is how you calculate the variance, right? So it is up to halfway to the variance. In the variance, you will finally divide with the total number of samples, right? That step you don't have to do. You have to find sum of squares. So sum of square means you have to find the mean. You have to check the difference of every value with the mean, and then you have to sum it up, right? So this is how you calculate sum of squares of each group separately, right? Once you make each group separately, you have to add it. Now this value 2330 is your sum of squares within group, because you are calculating separately for control for treatment 1 and treatment 2, right? Now the other column which you need to calculate is total sum of squares. So total sum of square, what you do is you take a mean of all the values all together, not just C but C, T1 and T2. So in this case you have 30 values, and then you take a mean of all the 30 values, and as same that each value should be subtracted with the mean value in order to get what? X minus mu. That is, mu is the mean here and X is the value for every data point you have. Once you have that, you square it and then sum it. So this will give you total sum of the squares. Now the total sum of the squares is how much? 29871, and sum of squares within group is 2330. So if you put in the mathematical form, the mathematics for this, if you put the value of total sum of squares and sum of squares within group, you will be able to find sum of square between group, right? Now sum of square between group, how will you find? You subtract the total sum of squares with sum of squares within group. This is what it is done here. If you will see, if you double click it, you will see that the total among group is subtracted with the total group, and the value what you get is sum of square between group, right? Now you should understand this particular here is that once you are getting this sum of square for between group and within group, you have to calculate the variance, right? Because at the end of the day, in the ANOVA, you are making the ratio of variance. So to make the variance, how many groups do you have in total? You have 3 groups. You have control, you have treatment 1 and treatment 2, right? So the total, sum of a square between group, which you calculated by subtracting the total square minus within group square, that has to be divided by 2, because that is your total degree of freedom. Because you have 3 samples and degree of freedom will be 2. So you divide your sum of squares between group divided by 2 in this particular column, right? Same degree of freedom within group, how many within group you have? So within group, total number of samples you have 30, right? 30 in 3 groups. So 30 minus 3. If you have one group, that is n minus 1, that is 10 minus 1, 9. Similarly, for other group, 10 minus 1, 9. And for third group, 10 minus 1, 9. So altogether, for 3 groups, you have 27. So this is degree of freedom, and you can divide the sum of squares within group with 27, right? Now, once you have these 2 values ready with you, this we will put it in the algorithm or in the function of the ANOVA, that is Fs. We will calculate Fs, and Fs can be calculated how? Variance among group divided by variance within group. Now variance among group here is 13770 and variance within group is 87 or 86.30, whatever you say, right? So this is your value 159.5549, right? Similarly, we will check the F-test distribution. So for F-test distribution, I hope that I have given the link. Oh, F-test distribution is the same what we have seen here in this particular Wave distribution table is already there. Now you match this. So how would you find the numerator and denominator? You will find 2 because you have 2 sample group, and then you have 27, right? Within group, within group you have 27 degree of freedom, and total group is 2, and the value is 3.351. So the FS value based on the distribution table is 3.351, right? What do you find here? The FS value is indeed greater than 3.351, right? Once the FS value is greater than 3.351, it assumes, or it says, the difference between the orbit among the 3 conditions are real and your null hypothesis is rejected, right? Now let us match this with the past. What we will do here, if you can go and check your folder, there is already a one-way ANOVA for F test. Oh no, this is for first data. Let us make a new file. We will open past. And since the values are derived from this particular data set, we will simply paste it here. And then in column attribute, since the first one is group, you make it as a group, and then compare the data set. You go in univariate and do ANOVA, several sample test ANOVA, right? Now, once you do several sample test ANOVA, it will do one-way ANOVA, and you can check the difference between the group we have calculated 29872. You can see here 29872 or 1.6, whatever. Among group you have, within group you have 2330. Within group you have 2330. So this is how you calculate the F test for ANOVA. And at the end, you also see that past also is performing Levin's test for homogeneity of variance, which indeed is not significant. So it means that your data does follow the homogeneity of variance. And then you have a p-value of less than 0.05, right? Also, if you can match, if you want to match completely, you will see that the Fs what we have calculated is 159, and Fs what the past has predicted is also 159. And then you will see that the past also says that that considering the significance or the alpha value we have taken as 0.05, the samples do have real difference, and it rejects the null hypothesis, which says that there are no real difference between the or among the 3 different groups, right? So this is how you do one-way ANOVA. Two-way ANOVA is also done in the same way. I have provided a data set where instead of taking just control treatment 1 and treatment 2, I have given 2 data sets. First can be considered as, for example, in this set, that you have one particular temperature, second temperature, and then you have the third temperature, right? Now, in this temperature, you have conducted a multifactorial experiment where each temperature is also having a triplicate of different pH conditions. If you remember this particular example which I have showed on the day 2, that not only the carbon dioxide, you are also providing the temperature, and this becomes a multifactorial experiment where you have 2 independent variables. One is carbon dioxide, second one is temperature. Now, how will you do the data entry? You will have to do the data entry. Okay, here I have written pH, but anyway, it's a function of, that will happen once you induce the carbon dioxide. So it means that you have the three different temperatures and then you have three different pH. And let us suppose that you have checked for antioxidants, so you have got the values now. And F test will be similar, like each group will be tested as we have done over here, and whichever is the lowest and the highest variance will be compared, and the F test for the homogeneity of the variance will be calculated, and then you can do this in SPSS. I will show you how, right? But before to go to two-way ANOVA, okay, it is important to understand the concept of post-hoc test. So if you remember that I talked about post-hoc test in ANOVA, because this FS, that is among group by within group variance, is indeed telling you that there is a significant, or if there is a difference between the groups, but it will not tell you that whether the, so in this particular example, can you tell me that whether the difference is coming between C to T1 or between T1 or T2 or between C and T2? It is difficult to say with this just with ANOVA. So in that case, what we need is also a post hoc test. So post hoc test is done when you don't have any prior assumptions or a hypothesis, and randomly you want to know that which group is having the significant difference, right? So in this case, you have example of group A, B, C, and D. In our example, we have only three groups, group A, B, and C. So if you have 4 samples, you have 6 different comparisons. If you have 3 samples, you have 4 different comparisons, right? How many comparisons? C to T1, T1 to T2, and C to T2. So basically 3 only, right? But these comparisons will be done by the post hoc test. And one of the most prominent post hoc tests which people are doing is a Tukey's test. And Tukey's test is again dependent by comparing the mean. So by comparing the mean and the variance of C to T1, C to T2, and T1 to T2, and C to T2. So 4 different combinations. So in that way, it will tell you where actually the significance are lying. It means that which particular condition is having the real difference among the samples you have for the ANOVA test, right? So this is the meaning of post hoc test. That also I will show you in past now. So you will see here that once you do the one-way ANOVA, you have the Tukey's pairwise test, right? So in Tukey's pairwise test, you will see control is, so control, of course, control to control, treatment to treatment, and treatment to treatment will be blank. But control to T1, you have a significant difference because you have minus 0.00 something value, right? It's less than 0.05. Similarly, for control to T1, T2, you have significant difference. But when you go with T1 to T2, it is 15.49, right? Or you just go with control to T2, that also does not tell you that there is a significant difference, right? So that's how you do the with the different what do you say, different functions. You can change the values and you can have a look at where actual variations are lying within the data set, right? That is the Tukey's test for post hoc. Let us do this particular thing in SPSS and observe the difference. The data set is already provided to you, which is labeled as one-way ANOVA. Okay, so what you need to do is you have to go in analyze. I am not going into descriptive statistics and all. I am just directly going to ANOVA one way, right? One way ANOVA. And here again, your factor is your treatment and your variable is your dependent list. You can choose the post hoc test. So as I said that in most of the case, you do Tukey's test, right? Now, there is another assumption which you have to consider, what if, because SPSS does not do the homogeneity of variance before, so what if the data is not following the homogeneity of variance? In that case, you have to choose any of these four post-hoc tests. One of the most common one in this case is the Games-Howell test. So we will check, we will tick that also, and we will continue. Now, in one-way ANOVA option, you have the descriptive analysis, you have the homogeneity of variance, and then you have the Welch test. So I will explain what this Welch test is. Once you click, you will get the homogeneity of variance. So again, homogeneity of variance is done with the Levin's test. Now in this Levin's test, what you will see is that all four of them are not does not have a significance value less than 0.05. So it means that our data do follow the homogeneity of variance function of, or the assumption of ANOVA. So it means the data is ready to go with the one-way ANOVA. So in that case, we will leave this robust test for equality of means. I will tell you what it is. You will directly go in ANOVA and you will see that there is a significant value, a significant difference, right? How this ANOVA table is calculated is the same how you calculated in the Excel sheet. Here also the data is very much comparable, maybe slight variations, but mostly comparable. Here between group variance is 27541, right? Here between squares, some of the squares, we also have 27541, right? Similarly, within group it is having 2330. We have the within group sum of a square value as 2330, and the total is 29871. We also have got total as 29871. So now you will see that how you can perform the one-way ANOVA in the Microsoft Excel, which is very much similar to what SPSS has generated as a result. Also, you can check that the degree of freedom between group is 2. Of course, you also have 2 because anyway you have only 3 samples. Then within group you have 27 because overall you have 30 samples within the 3 groups. So you have 27 as a degree of freedom. And then F test is 159, FS value. You also have got F as 159. The table is not giving you FC value, FC critical value, but then you can check online the link which I have sent, and then you can match with the in the table you will see the value is 3.551. So it means that ANOVA is saying you it's a significant difference. Now you can go in multiple comparison in the post-hoc test, and since the data is normally normally distributed and following the homogeneity of variance, you do not consider Games-Howell test here. You just consider the Tukey's HSD, and then you will see that all the conditions are showing the significance over here. That is control to treatment 1, control to treatment 2, treatment to control, treatment to 2, treatment 2 to control, and treatment 2 to treatment 1. So all the values are significantly different, right? So in here, suppose in some cases what will happen is that if the treatment 1 and treatment 2 are not significantly varied, this value will be more than 0.05, right? So this is how you check the assumptions of ANOVA and perform the ANOVA test in SPSS, and this is what Tukey's post-hoc Tukey's test means. Okay. Since we have very less time remaining, I am not performing two-way ANOVA. You can anyway find it out that how to perform the two-way ANOVA. It's nothing more difficult. You can go in analyze, and then you can go in general linear model, univariate statistics, and then you can consider your oh, so the data is not there. I mean, I don't have the two-way data here in the sections and SPSS here. Otherwise, you can just take the variable and other variable in the dependent variables and treatment in your fixed factor and run the two-way ANOVA, right? So this is how you do it. I'm not going in that, but instead what I will show you is that what happens when you do not have the data which is following the parametric assumptions. In that case, you have the similar test in non-parametric test, as Aditya has already explained you. In this case, if you have two groups which is following all the assumptions of parametric test, you do independent sample t-test. Otherwise, in the non-parametric equivalent is Mann-Whitney test, which we will witness now. If you are doing ANOVA, then you can do Kruskal-wallis test if the data is not following the assumptions of parametric test. So Mann-Whitney test follows the U statistics. I don't know if you have observed till now that independent sample t-test is having the name of the test is t-test. In the ANOVA, we have f-test. In the Mann-Whitney test, we have u-test or z-test. And Kruskal-wallis test, we have KW, that is a different test, right? So you will see that you have learned in this particular workshop f-test, t-test. Now I will explain you what is u-test and z-test, right? So bear with me for next 5 to 10 minutes. So in Mann-Whitney test, what happens? You are not following. So in the spreadsheet, if you open that MWU test, Mann-Whitney test, you see the data set is having unequal number of variables or the reading points. One is having 10 and one is having 9, right? So what do you do in this case? The formula on which this Mann-Whitney test works is N1 into N2. It means that the number in the control and the number in the treatment multiplied plus N1, that is again the number in the control, and then R1. I will show you how this R1 comes, right? And either U or U prime, any of this is having larger than the UC value. For UC value, again you will have to look into the table as similar to t-test and f-test, and then if the value is larger than UC, then you reject the hypothesis and the difference is real, or whatever your hypothesis, alternate hypothesis is correct. So in this particular non-parametric test, you arrange your data of control and treatment, right? So for all the control I have given 1 and for all the treatment I have given 2. Now you paste this control data here and then treatment data here, right? You select this particular 3 column using the function of sorting. Using the function of sorting, you sort the data from largest to smallest or smallest to largest, right? Now that you have given the number for all the data and 1 stands for control and 2 stands for treatment, you are not losing the data or you are not mixing the data of 2 particular groups. So it means that you still have the possibility to know that which particular data is coming from which group, right? After that, what you do, you sort it with, after you sort it with the group, you give it rank, right? Now, once you give it rank, what will happen? It will come in 1, 2, 3, 4, increasing or the decreasing order. After that, you sort it again with the grouping, or you can leave it as it is, doesn't matter. So what is important, this R is your rank. So rank of the first group. So how will you find the rank of the first group? In the column which you will see here, the sum of the rank. So since in my particular example, all the 1 is in the top and all the 2 is in the bottom, it may not be true in all the cases when you perform this Mann-Whitney test. In that case, what you do is that you calculate, you do the sum of the rank of the group 1 and do the sum of the rank of the group 2, and that is going in the equation. Now you have N1 into N2. So N1 is the number in the control and N2 is the number in the treatment. You have written here in the yellow box. You multiply it, then you have this particular function, that is N1 in bracket N1 plus 1, right, divided by 2. So if you see here, I have already done it in this particular case, right? So N1 into N2, right? I hope that it is clear now. No, not in this one. This is Z test that I will explain later. So here you will see that this particular calculation is already done. That is N1 here in bracket N1 plus 1, N1 plus 1 divided by 2, right? Now, when all the variables or all the data point in the formula is ready, you put it into the formula. So N1 into N2, so that is 90 plus N1 in bracket N1 plus 1 by 2, that is this value 55. So you plus that and then you subtract it with R1. So R1 is what? 55. How you get R1? R1 you got it. R1 you got it by subtracting this, by summing this rank of all the control treatment, right? So you got a value of 90. Similarly, you again derive u prime. So u prime is n1 into n2 minus u. So basically it will give you u2 or you can say u prime. So n1 into n2 is nothing but 90 over here and u value which we have already found out 90. So it is giving you 0. Now any value whether u or u prime is if it is greater than the uc, how will you see UC? UC, there is a table which I have given in the Excel sheet here, just for saving time again going into the web. However, you can search the U distribution table and it will come. So now you have N1 and N2, and then you have N1 and N2 how much? You have N1 and N2 10 and 9, right? So UN1 is 10. UN1 is 10 and UN2 is 9. So this value is 11. Now 90 is greater than 11. That is why the null hypothesis is rejected and the difference what you are observing is a real difference. So it tells you that the difference between the control and the treatment is a significant difference, right? And that also you can check with the past. I will show you. So what I will do is that I will copy this to data. And then you paste the data. Now you select this two and then you run univariate. And you have sample two tests, and then you have this Mann Witney test. Now this Mann Witney test is again calculating the same way how you calculated with the Z value, and then so here it is doing Z test, which I will again explain you quickly, which is also based on U test. This is the function of the Z test, that is U minus U prime, U bar minus 0.05 divided by S, where U prime is N1 into N2 by 2. So U bar you calculate N1 into N2 by 2, that is the U bar, and then here you calculate the S, that is N1 into N2 whole square root, N1 plus N2 plus 1 divided by 12. So this value again you will calculate because you already have N1, N2 everything. After that you found a Z value of 3.63, and indeed past is also finding 3.63, and any value in the Z test, if it is greater than 1.96, then it's a significantly or not significant, it's a real difference, you can say. It means that your null hypothesis is rejected and the difference what you are seeing is a true difference. So this is how you define the U test and Z test for Mann Witney. Similarly, for the non-parametric test, you have the Kruskal-wallis, or for the paired end you have the Wilcoxon rank test. So all those non-parametric tests follows this rank order, and the calculation is more or less in the similar way. But of course, you have more than two groups there, so it's a kind of mix with the ANOVA and with this ranking value which I have shown. we are not going to do the ANOVA, repeated ANOVA, or we are not going to do the non-parametric ANOVA test with the software, but I can show you how it does when you are using the past. So you have a data, one-way ANOVA. This particular data, you copy it, you go in past, you take a new sheet, and then you paste it here. After that, you click on column attribute, you do a group, and then you close this. Select both, go in univariate, ANOVA, several sample test ANOVA, and then as you find out for the, all the tests in the one tab itself. So here you have Kruskal-wallis test, and the Kruskal-wallis test says that there is a significant difference between the sample median. So what you need to understand is it has done the value, Kruskal-wallis test is on the median and not on mean. As Aditya was saying, that most of the non-parametric tests are happening on the mean. However, not true with the Mann Witney, which is working on the mean value. Okay. So here in this case, Kruskal-wallis test is more appropriate for one-way ANOVA, and you will see that it's a significant difference between the sample median. Okay. So this is how you do the ANOVA. One last thing, what happens when you have a paired or the repeated samples? So paired or the repeated sample means what? It means that sometime when you do any experiment, you take the measurement before and after the treatment, or you do any experiment where you are continuously taking the readings at equal interval of time, or otherwise sometime if you are working on twins or working on the subject which is shared. As for example, if you want to take some observation that a person is listening from left or the right ear, where you can't make any differentiation, it's not independent. So in that kind of situation, you put paired or the repeated samples test, right? I am not going to show you that how you can perform the repeated measure analysis of variance for repeated measure ANOVA or the Friedman test, but definitely I will show you how the paired t-test can be done. So in the paired t-test, what you can do is, again in the Excel sheet you have the formula. So suppose in this particular example you have any seedlings where you are giving two growth factors. First you are giving one growth factor, and after some certain days you are giving another growth factor by removing the growth factor 1, right? So you have 10 sample points, and then you have the growth factor after giving the growth factor this measurement, and then you remove the growth factor 1, and then you given the growth factor 2. Now, what is your hypothesis is that whether the real growth is happening even after adding the GF2, or simply you want to check that if the effect of growth factor 1 is continuing even after removal of the growth factor 1 and when you are putting in growth factor 2. So now that you will see that two growth factors are given in the seed and you cannot separate it out. This is a paired paired data. In this particular case, what you should do is you should make a difference by subtracting the GRF2 to GRF1, whatever your two variables are, whichever you are measuring, you make a subtraction. Once you do the subtraction, you will find the difference. Now, you take the mean of the difference. Once you take the mean of the difference, and you already know that how you can calculate the standard deviation and standard error. So this t-test, which is the paired t-test, is having a function, or the formula is that the mean of the difference divided by standard error. So mean over here of the difference is 8.45, and the standard error is 1.56. What you do is that you do division, or you divide the mean with the standard error, and you will get a value that is 5.41. Similar to how you have this this U distribution table. I already showed you that there is a T distribution table, right? So similar T distribution table you will open. This is F. This is okay. This is T distribution table, and now considering the uh, degree of freedom 9, right? You will check with 0.05. So two side p value 0.05 and then 9. So you will come across a value 2.262. Now, if the value of t is greater than 2. I mean with the TC value, critical t value, which is there in this case, so you reject the null hypothesis and you can say that the difference is real. So this is how you do the paired end test. Similar kind of things are there in the repeated ANOVA, but of course again you have more than two conditions over there, so you have more variables and calculations may vary slightly. But for the paired end t-test, you do this. You take a difference of the group, I mean two variable, you take a mean, you take the standard error, you divide it and then you compare it with the T critical value from the statistical books or anywhere which is available in the web, and then you compare. Based on that, you can reject or accept or reject the null hypothesis or accept the null hypothesis. So this is all about the statistical test with the practicals and demonstration